I'm making a video for the final exam part 2 answers. I will be short. So question 1 gives you a bunch of variables, and part A is which ones are continuous. So remember, continuous is like a regular number that can have fractions and decimals, and where 0 means there are none there, right? So that's the most used variable is the continuous variable. So SPSS calls them scale. Other people call them ratios. But, I stick to the word continuous because I know what that means, right? It's actually a calculus term. But basically, it just means a list of numbers that can have fractions and decimals less than 1 values. Okay, that's all that means. Okay, so the answer to this one is height, weight, age, annual income, distance driven daily blood pressure. So again, that's the continuous. Okay, so which ones are categorical? It looks like, let me get these all on the paper where you can see them. Please hold. There we go. So categorical puts people in groups, right? Also called nominal. But gender, whether they use alcohol or not, their ethnicity, got ethnicity twice, don't know why, and which political party they are affiliated with, and which ones are ordinal. So if you see the word level, that tells you right off the bat that this is an ordinal variable. An ordinal variable is like a staircase, right? 1, 2, 3, 4, 5, 6, 7, 8. Normally, if it goes over 10, it's not ordinal. You just make it continuous. But ordinal has no decimals, no percents. Okay, so, and think of a Likert scale, right? 1, I hate it. 5, I love it. And all the numbers in between measure that. Okay, so number 2, we're going to make a pie chart from the variable name ethnicity. So we're going to pull up our SPSS. And there's ethnicity right at the top. Let's see what we're talking about here. We got 1, 2, 3, 4, 5, 6 groups. Cancel. I'm just going to go here. Legacy. What am I looking for? Pie chart. And summaries. And get in there, you. Boom. And I want to find the slices by ethnicity. And you can get kind of fancy on here. Let's see what else we can do. We can click OK. And it should switch over here. And this is our pie chart, right? So the number 1 chunk here is either this pink one of Asian or the green one, which would be Hispanic. Okay, that's it right there. Next question. Make a bar graph of type of therapy. All right, type of therapy, back here. And this one, I'll just use the chart builder. And I want a bar graph. So I'm just going to click the plain one up there, put it up there. And let's get these over so you can see them. And type of therapy goes into the x-axis. Beep. And that's it. Click OK. Can't see it, but it's down here. Click OK. Boom. And there's type of therapy. So far, so good. All right, histogram from IQ scores. Histogram from IQ scores. And again, I will probably just use, you always have options with everything. So the legacies, dialogues, right? I could do the histogram this way. And what was it, IQ scores? Yes. And that's all you got to do with this one. And there's your histogram. You could have done this way. We could have gone to analyze, descriptives, explore. IQ scores over here and pick the plots. There's a histogram right there. There's another way to do a histogram. They should all be the same. There it is. And one more quickie, we could do the chart builder. And you go down here to histogram, just drag one in. Beep. And then you type in IQ scores. And they're all the same, right? And no, that is not normal. No question about it, right? So looks like you got some outliers over here, but again, it's just not normal. Not normal. Okay, so all right, we did the history. Okay, so number 5. What is the average IQ for Hispanics only? Okay, that means we're going to do a split file. We could have done select cases, but split file is the fastest. So we want IQ scores for Hispanics. So we could go either way from either one of these data sets. But I'm going to go to File. And you can't see it, but it's right off the screen here because it says split file. And we want to compare the groups by each individual group. We're going to do ethnicity as the splitter. So for every level of ethnicity, we're going to get whatever we ask for next. And so we're just going to do, I'm going to go easy with frequencies. And it was IQ scores. And we wanted basically just the mean or the average. So we'll make this quick and painless. So there's the white IQ, Hispanic IQ, which is the one we want, 102.7. But it's got them all, African American, Asian, Middle Eastern, and other. Got that? So it's 102.7. Again, there's the answer for Hispanic IQ scores only Hispanic. Okay, next problem. Okay, don't forget to unsplit the file, right? We got to unsplit the file. So question 6 is, we want the average IQ scores for white, Hispanic, and African American as a single group. So in other words, we're going to take the white, Hispanic, and African American people and lump them into one giant group, regardless of their race, and we're going to find that single group's IQ scores. So let's go back here. And number 1 is we're going to unsplit the file. Again, it's off screen. Sorry about that. But just hit reset. Click OK. Now we're going to select cases, but we don't know what the cases are. So let's go back and read the problem again. White, Hispanic, African American. So we're going to go into our data set and see what numbers white, Hispanic, and African American are. So that's 1, 2, 3. Those are the only ones we want. 1, 2, 3. So we don't want 4, 5, or 6. So we're going to go to data, select cases. Again, it's off file here. Sorry, I don't want to mess around too much with it. Select cases, and we're going to use on condition that, if condition is satisfied, if, and we want ethnicity. And if it's less than, I could put less than or equal to 3, but I'm lazy. I'm just going to put less than 4, which means 3, 2, and 1 will be used, which is the group we want. Okay, so click OK. And now we can go either way we want. Let's do descriptives this time. And I just want the, what was it, IQ scores again? Boom. Okay. And it's going to treat all that whole thing as one giant group. And there it is right there, 102.50. There it is right there, okay. Next problem. A one-way t-test. That's what tells you what to do, one-way t-test. Significant difference between the sample mean from the data file IQ versus a norm of 100. So again, don't forget to unsplit the file and undo the select cases. So back up here, boom, down to select cases, and just hit reset. So the data's back to normal. So we're doing a one sample t-test. Analyze, compare means, because that's what t-tests do, right? It compares the means. One sample t-test, and we want IQ. That's the variable we're testing. It's going to take the average of that variable that we have, and it's going to test it against the number 100. That's the stated norm. Oops, 100, not 200, sorry. Click OK. So So there's the sample of, there's the mean of the sample, of our data, of our variable named IQ. That mean is 102.46. That's for everybody. And we're testing it against Z100. And according to this one, it says there is a significant difference between the two, right? So our t-score is 2.73, which means that there's 2.73 standard deviations away from the sample mean of 102 and the stated norm of 100. That's all there is to it. Wasn't that easy? Yes, that was easy. Okay, so what was the null is there's no significant difference between the sample mean and a stated norm of 100. The alternative is there was a significant difference, right? And it was a one-tail or a two-tail test. It's a two-tail because we're just looking for is there a difference. We're not seeing if one's higher or lower than the other. That's called directionality. So this is a non-directional test of significance that makes it a two-tailed. Calculated p-value was 0.009. And the critical, a lot of you guys missed this one on all of them. That was the easiest one there was. The critical p-value is always 0.05 unless somebody else tells you. So it is assumed to be 0.05. That's the critical alpha tells you to reject the null or not. So your calculated p-value comes from the test, from SPSS, or whether you do it by hand. This is the calculated p-value. And if this number is less than this number, you reject the null. So you reject the null. And yes, there is a significant difference between the mean of our data set and the stated norm of 100, even though it wasn't very big, but it was significant. All right, coming up. Next problem, run an independent t-test. Independent means they're two separate groups. So our groups are male and female. So the question is to see if females have significantly higher. You see the word higher? So we're picking a side. We're assuming that females have higher IQ scores than men. That makes it a directional. You're picking a side, which means we're going to run a one-tailed test of significance. I'll give you that answer right now because the word higher is there, right? Higher, greater than, less than, more than. That makes it a one-tailed test, right? Because we're comparing one group to another, and we think one is higher or lower. Okay, so let's run that test. So we're going to go to Analyze, Compare Means. Again, that's what t-tests do, independent samples. So let's get our gender is our grouper down here. And I believe we used 1 and 2. If not, the machine will tell us here. And we want IQ scores as the test variable. That's the DV. And I think that's all we need. So there's all our information. So the averages are real close to each other. So don't expect a significant difference. So a lot of people make this mistake. These first two columns, right? Levine's test for equality of variances. That's one of the assumptions, right? That the variance between each of the little subgroups between men and women, the variance of the IQ scores, in other words, the spread of the IQ scores for men should be about the same as it is for women. That's what the equality of variance test is. We call it the homogeneity of variance, which means the same thing. So that was not significant, so that means it was not violated. That's not what we're looking for. We're looking for this, the t-score. Boom, 0.151. The rule of thumb is if t is 2 or greater, or -2 or less than, then you're going to have a significant difference. So there's your sig value. It's not even close. Okay, so let's answer them questions. The null hypothesis is there that the means of the males is equal to the females, right? There's no significant difference between the means of the IQ scores between the groups. Alternative is there is one. In fact, that should be an A, not an O, right? Null hypothesis, right? And it is a one-tailed test because we picked the side that females are higher. And the p-value was, where are you here, boom, right? 0.881, which is nowhere close to 0.05, so it was not significant. And we have to divide it by 2, right? Because this is a two-tailed test. What this is, right? It gives out two-tailed p-values, but it's a one-tailed test, so all you do is you divide it by 2. A lot of you people missed that one, but I think I might have given it to you anyway. Just remember, if it's a one-tailed test and they give you a two-tailed test of significant, divided by 2. And it was still not significant, so we do not reject the null, and there is no proof. The data does not support that females have significantly higher IQ scores than men. Okay, so next one, we're going to run a paired t-test, see if there's a significant improvement between the stats pre-test and post-test. Now, improvement. Think about this for a second. So if you take a pre-test and everybody does poorly, and then they teach you 2 or 3 weeks of statistics and they give you the same test, the post-test later, and it improves, that means it's going to go up. That makes this a one-tailed test. Got it? We're expecting improvement in the post-test. Again, that makes this a one-tailed test of significance. So let's run this real quick. Analyze. And it's a pre and a post-test. That makes it a paired t-test. Compare means. We're going to do a paired sample t-test. And we're going to put in the pre-test for stats and the post-test for stats. And that's all you got to do. Click OK. So there's the mean of the pre-test, and there's the mean of the stats post-test, right? So it went up about 6 points. That's a pretty good change, but we're going to double check, and we're gonna look at the outcome. Don't look at the correlations. We don't care about correlations. But here's the actual t-test results. There's your t, right? Let's get this on screen so you can see it. There's your t-test score. Degrees of freedom, and there's your significance test. So what you should do is divide that by 2, right? You know this is a one-tailed test. That's a two-tailed significance. So if you divide it by 2, you get what? 0.0135 or 0.104, whatever you want to do. Let's go back and answer those questions. Null is no significant difference between a pre and a post-test. And again, that should be an A. Sorry about that. And the alternative was the mean of the pretest. The pretest mean will be less than the post-test mean. That's what they're trying to say here. And it is a one-tailed test because we are hoping that the post-test is greater than the pretest. And there again is the calculated p-value. Let me see if I can't get this over a little here before you. Boop, 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 boop. But that's a two-tailed. We got to divide that by 2 to get a one-tailed, and that comes out to be just rounded off to 0.14. Critical alpha again is 0.05. Again, I was stunned by how many of you guys missed that. Just remember, critical p-value is always 0.05 unless somebody says, no, we're going to use 0.01, or no, we're going to use 0.001. But we don't do that in this class. Okay, so critical is 0.05. Do we reject? Yes, because our calculated p-value of 0.014 is less than that. So we reject the null and state that, yes, there was a significant increase in stats post-test scores over the pre-test scores. Wasn't that easy, cheesy? Moving along, number 10, we're going to run a chi-squared test. It's actually a chi-squared test of independence, and we're looking for a significant association or relation between 2 categorical variables. Only 2 categorical variables or nominal variables. Ethnicity is a nominal variable, as is type of therapy. Analyze descriptives. Now, the chi-squared tests in SPSS are called crosstabs because the British guys invented SPSS and they call them crosstabs, and we could live with that. So let me try to get this thing all on the same screen so we don't have to bounce around. Please hold. All right, here we go. So what was it? Ethnicity and types of therapy. So it doesn't matter. One can go in row. I could switch these around. It wouldn't make any difference whatsoever. So you put the 2 categorical variables, one in row, one in column, and we go to statistics. We want the chi-squared test statistics, the phi and the Kramer's V. Go to cells. We want expected if the null were true. And we want to standardize residuals. And lately I've been using the column percents because I don't have to do it by hand. But that's the rest of them. And then we're going to click OK. It's down here off screen. And here's our results. So what we're looking at is, first thing you look at is this, right? Your chi-squared test, right? This Pearson's chi-squared test. This is the sig value of the Pearson's chi-squared test. And it's a two-tailed test. Everything from now on, the two-tailed test is the one we're going to use. That one-tailed test of significance is only for t-tests, so don't worry about that anymore. But it's not significant. Okay, so let's go back to the output here. The sig value was 0.371. That's the calculated p-value. And it was nowhere less than the critical p-value, 0.05. Okay, was there significant association? No, there was not, right? So since there was no significant association, we don't have to do any of these other answers. Okay, next question. All right, we're going to run a correlation matrix on the variables attachment, depression, anxiety, and relationship satisfaction, and identify the strongest and the weakest. Okay, that should not be too bad. So we're going to go to correlate. Got to get the names of them. Okay, attached, depressed, anxiety, and relationship satisfaction. We're going to go to analyze, correlate, stick them all in there, bivariate. And it was, what was it? It was attachment, depression, anxiety, and relationship satisfaction. Okay, attachment is it measures how strong a person feels he belongs to something, right? Like a family. Usually, you know, a person with strong attachment means he feels like he's part of a family, or she feels like she's part of a family. Depression is sadness. Anxiety is anxiety. Ooh. And relationship satisfaction, right? How in love you are with everybody. So this is a bivariate correlation, and you'll see down here on the bottom that it automatically gives you the Pearson's. So if the data is ordinal, if one of the variables is ordinal, we're supposed to use a Spearman's, or if the data is horribly skewed or something, it makes more sense to use a Spearman. The Spearman is a non-parametric version of the Pearson, but we're going to do them both just to show you that the difference between the two is minimal. All right. So the top one is the Spearman's, and here's the list of correlations between everybody. And down here is the, where's the Pearson's? There's the Pearson's, right? Pearson's, it doesn't call it anything, but there's the ones we're looking at here. So we're looking for the strongest. The strongest, there's one right there, right? 0.622. That's pretty dang strong. That looks like the winner. So this is the relationship between relation satisfaction and attachment. Relationship satisfaction and attachment. Yeah, 0.622. And the next one is the weakest. Let's take a look. There's one. Depression and anxiety. That's pretty low. Is there anybody lower than that? Again, we're just looking at the top row, right? So the top row is the actual correlation. The sig value row is the significance value of the correlation, right? So I see the lowest one is 0.078. I don't see anything smaller than that. I don't think so. Nope, that's it. So it's anxiety and depression. Again, I just made those numbers up. So that's the answers. Okay. Number 12, is there a significant difference in relationship satisfaction scores between the different ethnicities? So you're looking for difference between group means. You can't use a t-test because ethnicity has more than 2 groups, right? Ethnicity has a lot of groups. It has 6 groups. So we're going to have to use the grandson of the t-test, looking for group differences, and that is a one-way between group ANOVA. We're going to go to Analyze, General Linear Model. This is the way I like to do it. There is another one. Let me show you here. Compare means. There is another way to run a one-way ANOVA right there under Compare Means. But I like General Linear Model because it checks a lot of the assumptions for you. And I am lazy. So the DV is, I already forgot what the DV was. It was Relationship satisfaction. Okay, so relationship satisfaction is our dependent variable. It's our DV. And our fixed factor is your nominal variable. It's your ethnicity. And basically we want post hoc tests. Post hoc tests, you need at least 3 groups. That's why we don't run post hoc tests on t-tests, because basically these are all t-tests. They're very t-test-like. And we want options. This will check for, okay, that gives us descriptives. This gives us effect size. Remember, effect size is the percent of the variance that you can explain. And power tells you basically is if your sample size is large enough. And homogeneity of variance, that's one of the 3 assumptions, right? That the data fits a normal data set. The spread of the variance is pretty much the same across all the levels of your nominal variable. And the last one is independence of observation, which we can't check. So we're not going to worry about that. And I think that's it. Boom. So this is how many people we had in each group. Here's the means. You can see some big means differences in here. So that's going to be significant. Don't act surprised. And this is your Levene's test. This one right here checks for homogeneity variance. Did not violate. And there's your overall model right there. So your F score was 6.495, less than 0.001. Significant. This is your effect size, and that's your power. Let's get that over there so you can see it. And there's your power, right? So power, effect size, significance. So now let's go check the answer sheet. So what kind of test? This is a one-way between group ANOVA. The null hypothesis is there's no difference between the mean and the means of the relationship scores between the different ethnicities. And the alternative is there is a significant difference, and we found that there was. Did it violate the assumption of homogeneity variance? No, right? That number has to be less than 0.05. What was the F ratio? That's this. So in other words, what that means is that because it's a ratio is 6.5 times the percent of the variance is coming between the groups as compared to within the groups. So that is obvious that the difference in relationship scores is coming from between the groups, and that's why it came out significant. And the calculated p-value is less than 0.001. And critical p-value is always, again, so many of you guys missed this one. Don't ever miss it again. And yes, we reject the null. Was there significant difference in relationship? Yes, there was. What was the effect size? In other words, the percent of the variance in the DV that you can explain. That's by definition the effect size. And that's your partial eta squared in the ANOVA family. There's a lot of different types of effect size, right? There's R squared, there's Cohen's d, there's a ton of them. So each test has its own specific effect size, right? 42.5% of the variance of the DV can be explained by this model. Power was acceptable. Yes, sir, Bob. It was greater than 0.8. And so that this test was good. Okay. Next, a therapist wanted to verify that her work, a therapist, that means a psychologist, wants to verify that her work with her clients was indeed making them feel better. So she had 50 clients, and she wanted to measure their life satisfaction score before she started therapy. So that's what we call a baseline score. And then 2 weeks after a therapy, she gave them the life satisfaction again. And if her therapy was working, her life satisfaction score should have increased a little bit from the first one to the second one. And then later, 2 more weeks, after 2 more weeks of therapy, so after 4 weeks of therapy, she gave them a third measurement of life satisfaction. And then 6 months later, she wanted to do what we call a follow-up to see if their life satisfaction scores, if they went up, if they stayed up after 6 months. So that is a within group ANOVA or repeated measures ANOVA. How I know that is because there's only one group, right? There's no mention of a group that got this therapy and a different group got that therapy, right? There is no grouping in there, and there is a measurement. It's the same measurement that everybody has to take, and it's repeated. That makes it a repeated measure or a within group ANOVA. And here we go. We go to Analyze General Linear Model. This is a repeated measures. Dun, dun, dun. And we got 1, 2, 3, 4 repeated measures. You got to define them. So ours was baseline, down to all 4 of those, right? I can stick them all at the same time. And I'm going to do the estimated means, because you cannot, it will not do post hoc tests for within group ANOVAs for some reason. And then again, we want our options: descriptives, effect size, power. Get in there, you. And homogeneity variance is not an assumption for within group ANOVA, repeated measures ANOVA, but something we call sphericity. So we're going to get an error message about this, okay? Now, without twisting your heads there, sphericity subsumes homogeneity variance. In other words, homogeneity variance is part of the sphericity assumption. So let's just look at it as we go. Boom. And here's the means of the 4 repeated measures. And it looks like it did went up, right? When they started, their average was 51. And when 6 months later, it was 61. So it went up about 10 points, and it seemed to have stayed up. That's good. Now, we could look here at the multivariate test, but I taught you guys not to because there's so much more you can do with this one. But it is significant. So all that means is there's going to be a significant difference between those repeated measurement means. And this test is our test of sphericity, the Mauchly's test of sphericity, and it violated it. Okay, so that means not everybody went up at the same time. So this thing did violate the assumption of sphericity. And this is our factor 1. This is basically our source of variance table. Now, if the sphericity wasn't violated, we would use this top row. But since it was, we're going to use one of these other rows. I always tend to pick the Hunfeld. So we would use these numbers on the Hunfeld row to write it up if you're going to write it up. But you'll notice the F scores are all the same, and the sig values are pretty much the same. Everything's the same. Eta squared is the same, etc., etc. And let's see if we can get the power on there. Power. Yeah, powers are pretty close to the same. So let's answer those questions. What type of test? This should be a one-way within group ANOVA or a repeated measures ANOVA. Did it violate sphericity? It certainly did. And the F ratio, again, I'm going to use the Hunfeld. Doesn't matter which one. They're all basically the same. That's our F ratio, which means that 10 times the variance of the life satisfaction scores is between the repeated measurements instead of within one, a single one. So that's good. That's your F ratio. Calculated p-value less than 0.001. And right, that's the less than 0.001 is the calculated p-value. Again, the critical alpha 0.05. You're never going to forget that again. And yes, you reject the null. And did the data show that her therapy was working? In other words, did life satisfaction scores show any significant improvement over time? They sure did. Right? They started at 51.14. They ended at 61.66. That's an increase of over 10 points. So, yes. So what percent of the variance can be explained by the repeated measures? 17.7%, which is actually kind of high for this kind of test. And I think there's a power question coming up. Yeah, power acceptable. It certainly was. Boop. And, you know, again, I probably should have used the Geyser, or I'm sorry, the Hunfeld. That's the one I like the best. It's the friendliest one to researchers. It gives you the best numbers. So, and there's the power, which is fine. Yep. Okay, next to the last one. Run a multiple regression using the predictors of exercise minutes, sitting minutes, weight loss. Criterion variable is weight loss. So in other words, we're trying to predict weight loss using the variables calories, exercise minutes, and sitting minutes. So that shouldn't be too hard. Analyze, regression. Get in there, you. Regression. And we always assume linearity. It's up here off screen. Sorry, you guys, but it's linear. And the DV was weight loss, right? Boom. That's your dependent variable. And then does calories, exercise, sitting. Did I get those? These are the predictor variables. Do they predict weight loss? Yes or no? Okay, so statistics. Always do the right side. Again, this checks a lot of the assumptions for us. And plots. This is the hard one. This is the homoscedasticity. Hard to say. Harder to spell. And this looks at Mahalanobis. That's the no multivariate outliers and the rest of that stuff we don't need. Click OK. All right. There's our output. So let's go back to the answer sheet and let's see if I can't do it that way. Boom, 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 boom. Was it a significant model? Yes, it was. What that means is the ANOVA is significant. So if the ANOVA is significant, the model is significant. That's all you need to know, and yes, it is significant. And so what that means is at least one of these variables, either calories, exercise, or sitting, is a significant predictor of weight loss. It could be two of them, could be all three of them, but at least one is. That's all we need to know. And was calories a significant predictor? So since it's a significant ANOVA, we go down to the coefficients box and we look at calories, right? Calories, significant. It sure is. Yes, calories is a significant predictor. So is exercise. That's coming up here. Was exercise. It certainly was, right? The sig value of exercise in the coefficients box is significant. Therefore, exercise is significant. Sitting was not, right? There's sitting, it was 0.162. So the two predictors are calories and exercise, and not, sitting was not. So which one was the strongest predictor? We look at the beta weight. So the beta weight says exercise was the strongest predictor of weight loss. And what percent of weight loss can be explained by this model? That's your R squared value. That's your effect size. So roughly 40.8% of the variance of weight loss can be explained by how much a person exercises and how many calories they intake. All right, last one. Which of the following predicts quality of life? And oh my God, look at them all. There's a bunch of them. So what I was hoping you would do here is a stepwise regression. So let's see if I can't get them all at the same time. So quality of life is the DV. Go to Analyze, Regression. And again, linear, it's off screen. And we're going to hit Reset here. Boom. So let's see if we can't get them all. So money, family, work, friends. I think all of these, all the way down to quality of life. Is that right? Stick those in there. I'm going to double check real quick to make sure I got them all. No quality of life, just education. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14. So quality of life was not on there. Get out of there, you. Boom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12, 13, 14. Okay, I got it. So here's the trick to this one, you guys. Because there's so many of these, it probably makes a lot more sense to just do the stepwise. The stepwise, the software does all the heavy lifting for you. It will rewrite the equation only using those variables that are significant. It will kick out the ones that are not significant. Hallelujah. So, and again, we're just going to go to options. No, not options. I'm sorry. Statistics, we're going to go to these guys. And we did not go over any of the assumptions. I hope that's not a problem. And, okay, I'm not even going to mess with the rest of this stuff. And, oh, I forgot the DV. So that's quality of life, right? That's the DV, I think. Yep, quality of life. Okay, there's the DV. And now we're ready to go. Click OK. So So there's the means, which we don't really care for in a regression model or correlation. Correlation, this is important, but not that important at this time. So this basically tells us right here, model summary. This is the first variable that it found. It was enemies. Enemies is a significant predictor of quality of life. And in the second row here is the second variable. It added work. So according to this, only enemies and work are significant predictors. That's how that works. And the first ANOVA with enemies only is significant. The second model with enemies and work is significant. And which one is the biggest predictor? We go to the coefficients box. You look at the second row that has both of them in there. And it looks like enemies is the most strongest predictor of quality of life, right? So the less enemies you have, the happier you're going to be because it's a negative number, right? And these are all the ones that were not significant. So let's not worry about that. And let's go back and answer our final questions. Which of the following enemies and work? Use only those significant predictors. Which effect size? What was the effect size of the regression? That would have been this one, right? You'll notice it's row 2. Row 2 has both predictors in there, enemies and work. So the R squared is about 85.2%, which means that 85.2% of the quality of life variable can be explained by how many enemies you have and how much you like your job. Which predictor is the best? I think I just told you enemy, right? Enemies. So don't have any enemies. Now, that is the test. I'm sorry, it was kind of long, but if you think about it, we knocked this thing out in about 40 minutes. So I kind of hoped that you guys would get to that point where you can knock it out in 40 minutes as well. But again, I do this stuff every day, so it's a lot easier for me. I just hope you guys picked up on the big stuff. But that's it. I hope it helps. MGZ out.